We're just at the tail end of the first lecture on torsion, where we derived the membrane function that can be used for non-circular sections. And this last page, this handout, provides some relevant information and equations for different types of cross-section shapes you might encounter. So we talked a little bit about the triangle and hexagon and how the corners, right, the outer edge corners, at those points there will be zero torsion or zero shear stress. And the portions of the corners that will be inactive in resisting torsion are greater for smaller angles. So also, if we go back to the general membrane function as a reminder, right, we said that the slope on the outer edge is constant. And so we decided to set the value of the outer edge of that lambda function, it's okay, to be equal to 0 for convenience purposes, because all we really need is the volume that underneath that area, or underneath that membrane, to relate it to the applied torque, right? But if you look at the membrane and how it would be inflated, right? Even though we set the value equal to be 0 on the outer edge, that's where the slope would be the greatest, right? The slope would be the greatest at the outer edge, and then it would decrease to the top. And so this is consistent with what we are familiar with regarding torsional shear stresses, where you have 0 shear stress at the center of twist, and then the maximum shear stress is at the outer edge. So as R increases for a circular section, as R increases, the torsional stress increases to a maximum at the outer edge. And it's similar for non-circular sections. We just have a varying, quote, R, and we have to relate it to this membrane function. So just thought it was worth doing that little brief recap and relating it or tying it back to the easier to comprehend circular sections. So then the last bit on this handout is related to rectangular cross sections. So this you will definitely, I haven't picked out which homework problem you're going to use this for, but you will use this for one of your homework problems in the assignment that I haven't yet assigned. So here we have the formula for shear stress at point A, which is the point on the outer edge of the longer side, and also the equation for theta. And remember, theta is the rate of twist, right, where phi represents the total angle of twist at a given point along the length, or if you're considering the entire segment, right, at length L, phi is equal to theta times L. So the way this table works is it's based on the ratio of the dimensions of the sides of the rectangle. So A and B, lowercase a and b, represent half of the dimensions on each side. So A is specifically half of the longer side, and B is specifically half of the smaller side. And I just wanted to spell that out and clarify it because you might have some different notations that can lead to confusion in the homework assignment. So just stick to this rule for using this table anyway, where lowercase a is half the longer side and lowercase b is half the smaller side. Find your A over B ratio. Based on that, you get a K1 factor, a K2 factor. All right, so K1 is used in calculating the shear stress at A, point capital A. K2 factor is used in calculating the rate of twist. And then once you calculate the shear stress at point A on the long side, you can use this value to find your shear stress at point B. All right. All right. Any questions on that lecture? All right. So we're going to continue with this and see how it applies to open thin-walled structural members. And it looks like I also inserted homework 7 at this point. So in case you haven't seen homework 7 yet, this is what it looks like. You've got a circular beam problem. So cross-section shown here. And this problem, I will tell you right now, it's going to be kind of lengthy and tedious. So just as a heads up, you're going to be doing some repetitive calculations because you're asked to calculate the stresses at points A and B, so at the top and the bottom extreme fibers of that cross-section, for 3 different values of the inside radius, which is this lowercase b. All right, so the idea behind this problem is to investigate how those stresses, how sensitive those stresses are to the change in radius. All right, and let's see, and their commentary below here, right? So towards the end, there's some commentary that says, you know, a possible rule of thumb statement is that the straight beam equation for bending stress is reasonably applied if the beam radius to beam depth ratio is greater than 10. Right, so that's kind of what this is getting you to get a feel for.
Is an Excel spreadsheet said best for that, right?
You could use an Excel spreadsheet. I would just want to see sample, like I'm not going to grade your Excel spreadsheet, so I'd want to see sample hand calculations and, you know, make sure that you are clear about which values change for each iteration of B. Yeah. In your hand calcs anyway. And then for this problem, this is investigating strain energy. So I talked about this a little bit in class during that lecture. Here, you're looking at a cantilever beam with a rectangular cross-section and a uniform load. Given this relationship, we derived this in class, where you have the contribution from bending here and the contribution from shear here. So given this shape factor, the main part of the question is in B and C, right? So drawing the shear and moment diagrams is just a good thing to do initially to set up and get a feel for where you're going to have the maximum moment and shear values. And what those values will be in terms of Q and L. And then in part B, I'm asking you to analytically find the value for the ratio of length to depth beyond which moment becomes dominant. So for a small L over D, shear will contribute more than moment. So at what point does moment begin to take over that contribution, right? That's what we're looking for analytically. So just using, being creative with math and substitutions and things like that. Solve that by hand to get an L over D value. And then in part C, you're going to do a numeric comparison. So looking specifically to plot values for that represent the moment and the shear contribution. So there are a couple ways you could go about doing that, and I would accept multiple approaches as long as they're valid. I've seen, different folks take different approaches in the past. This is the only homework problem, by the way, that I have assigned every single time I've taught this class. So, and it's based on one of the foundational principles of my graduate research. So since it was tied to one of the lectures in this class, I thought it would be a great opportunity to turn it into a homework problem. All right, so, and then for part D, what percentage of shear strain energy contributes to the total for a length to depth ratio of 10. A couple ways you could report that. You could just plug L over D into the relationship that, from some point along the path to this solution and report it, or you could figure it out based on your numeric solution. So, that one's pretty simple. All right, and then you have the Castigliano method, applying that to two problems. You have a determinate problem and an indeterminate problem with a uniform load. So it will get a little bit involved with that uniform load, but you've seen enough in the class lectures to be able to apply that. So, any questions? Homework? Okay.
Is this due Friday?
This is due Friday. Mm-hmm. Yeah, I think that's what I wrote on the top anyway. It should be, yep, Friday. Okay. All right, so now torsion of thin-walled structural members where the cross-section is not closed, it is open. So since if we have a non-circular, any open section would be non-circular by definition. So we need to apply the membrane analogy. And as a refresher, we defined this stress function lambda, which relates to the shear stresses in the XY and XZ planes using those equations there. And we already kind of summarized this a moment ago, but go ahead and write it down. We said lambda is going to be equal to 0 at the outer edge of the cross-section. And the torque is equal to 2 times the volume under lambda. Also, the shear stress in the normal tangent direction at the outer edge is equal to negative partial derivative of lambda with respect to the normal direction. And we also have the second partial derivative of lambda with respect to y plus the second partial derivative of lambda with respect to z is equal to negative 2g theta. So these are all things that were determined in the previous lecture. And so applying this now to a thin section, or a thin segment at least to start, if we just consider a thin rectangular section first, that's subject to twisting about the center point, we would apply that membrane, all right, to the outer surface. And you see this membrane acting under pressure, right, where lambda represents the magnitude of that membrane, the outer edge of that membrane. And lambda varies, in this case, it varies along the z direction, but for a given point in that z direction, it will be constant in the y direction. So I'm going to clarify this right here. This is meant to be a lowercase t to represent the dimension in the z direction. All right, and that membrane is our lambda. So the idea here is we have a section where the length is much longer than the thickness, and that's when all of this would be applicable. So if we start with this equation right here, right, which is a differential equation. And applying two integrations, we would get lambda is equal to negative g times theta times z squared plus constant c1 times z plus constant c2. And I'm going to sketch this because I think it helps to visualize what we're doing here. So I'm going to sketch it in the xz plane. Call this t over 2, or I guess that would be negative t over 2, and this t over 2. So it's going to be something like that. So if we plug in positive t over 2 for z, we know lambda is equal to 0 at that outer edge, all right? So that's part of our definition from before. So we would say 0 is equal to negative g theta times t squared over 4 plus c1 times t over 2 plus c2. And then if we plug in our other boundary condition, which is negative t over 2, where lambda is also equal to 0, we have two equations with two unknowns. The unknowns are just the constants of integration. So solving, we would find C1 is equal to 0 and C2 is equal to g theta times t squared over 4. So our total solution then for lambda is g theta times t squared over 4 minus z squared, which is consistent with the formula for a parabola. And we also have our relationship to torque, right? So the torque is equal to 2 times the volume of the underneath the membrane. And so if we consider the fact that, right, we have this cross section is going to be constant along the length, we'll just make use of that, and it simplifies our calc a bit. So we have the volume, or the integration over the area of lambda, and we'll integrate from negative t over 2 to positive t over 2 of lambda times b in the z with respect to z. So that comes out to g theta times bt cubed over 3. So then we can relate our total angle of twist phi to the torque, right? So phi is equal to the twist rate theta times the total length L, and that's equal to TL over G and then bt cubed over 3. So that's essentially just solving this relationship for theta and plugging that in to this equation here. So this ratio of t divided by theta that I'm writing down here is representing the torsional rigidity. And capital L represents the length of the shaft in the x direction. All right, so at this point, we're going to define a term purely for convenience. And we're going to call it J star and set that equal to bt cubed over 3. So then we can write phi is equal to theta L or TL over GJ star. But it's important to remember that this term is not the polar moment of inertia for thin rectangular sections. There is a calculation for that value, and it's different, and it's lengthy calculation and kind of painful. In one set of my notes, I actually have it, so if anyone really wants to see it, I can bring it next time. But we won't need to use it because we're just using this term for the calculation. All right, so below I have a little sketch of the shear stress flow of that cross section. And we would find that the maximum shear stress will occur along the long edge. So where the z dimension, or where the z variable is plus or minus t over 2, all along that long edge there, you would have the same magnitude of shear, and that's where the maximum magnitude would occur. So that's assuming, of course, that these coordinates are placed at the center of twist. And my note below, or I guess I didn't finish writing my previous point, so say the max shear stress so that would be shear stress in the YZ plane, which represents that partial derivative of lambda with respect to z times g theta t. So your max shear stress would be torque times the thickness divided by J star. All right, so in my note below, shear flow is greater on the sides closer to the angle of twist. I'm pretty sure this word angle is supposed to say center of twist. So please correct that for your records. And this calc is an approximation for any non-circular cross-section. So a couple of things to keep in mind. The accuracy of this calculation will increase as the ratio of length to thickness of the segment will increase. And for a ratio B over T of about 10, that would be where you have, let's see, the angle of, or the twist rate, theta, and the maximum shear stress would calculate out to be roughly 6.5% lower than the exact values. So just to give you a point of reference of, how much accuracy you have for different B over T values. I'll note that here. So my last comment here, the results of these calcs can be applied to any narrow strip. It doesn't matter if it's a straight one like we looked at here, or if it's curved or bent. You can apply it to any narrow strip. In a moment here, we'll go through an example, so demonstrate the application here. Any questions so far? Okay. So on the next page, there's a handout that shows some values that are applicable to certain types of thin-walled open shapes. And so we specifically have the value for B, all right, which basically would represent, right, the not longitudinal really, it's not the right word, but the length of the segment versus the thickness. And then you have J star also spelled out here for each one. So you'll notice that for the sections that consist of multiple straight segments, that J star value is just the summation of LT cubed over 3 for each segment. So we'll apply that to this next example.
Question, and
Yes.
I think the math probably explains this, but I'm just not tracking. Why is it that the closer the side is to the center of twist, the higher the shear? Because it seems to me
Mhm.
logically that like, if we're twisting, even just say like a cylinder,
Mhm.
like the farther out you are, like the more it has to move and like the higher that shear force would be.
Yeah, I understand what you're saying. So it basically comes down to the fact that it's kind of, you can think of it, at least how I understand this or how I think of this, is it's sort of similar to those sharp pointed corners on solid section shapes, or, so if you have like a long, thin strip, right, the sides that are farther away from the center of twist will be less torsionally active.
Right. Okay.
Conceptually, I think that's the best way that I can think of to explain it right now. If I think of a better explanation, I'll definitely follow up on that. But yeah, and then as we go through the example, I think it'll also start to come together.
Okay.
Yeah. So yeah, so then when you think about it in the context of an entire cross section, or a composite of multiple thin strips together, right? You can think of it as, well, along the length side, that's where it's continuous section, right? Whereas that thickness part, that's not really going to be participating much in resisting torsion, right? Yeah, so it's really because the shear will flow through the section in this direction, right? If you're applying a torque in that direction, that shear flow will be through here. So that length is what's providing that continuous path for shear. You don't really get that in the thickness direction. Right, I mean, you do at individual element level, right? It's going to be something. Well, actually, no, not in this configuration, because if your center of twist is here, right, this whole section will be in that direction, so you won't really have that flow. When in this example we assumed that the center of twist was in the center of that section, right?
Right.
Yeah. So it's a little bit different from applying it to a piece that is composed like this, where the center of twist might be, off of the actual cross section. But yeah, good question. All right, so we have this cross section shape here, which is welded or fixed somehow to a plate on both ends. So then the plates can be twisted by a torque T. So we're asked to find the maximum magnitude of shear stress in that cross section, and we'll assume that we have a uniform shear modulus, so we don't have to worry about different material properties. So first we're going to look at the total cross section. And we're going to calculate that J star for the entire cross section. So that's just going to be the summation of the length of an individual segment times the thickness of that segment cubed divided by 3. So going through, starting at A, we have 20t times t cubed over 3 plus 12t times t over 2 cubed over 3 plus 10t times t cubed over 3. And at this point, I'm also just going to note that the first term is going to be J star for segment AB. That second term is J star for segment BC. And that third term is J star for segment CD. We will use those individual J star values later on in the solution. But first, to get the J star for the full section, we have that summation comes out to be 10.5 times t to the fourth. And so the rate of twist theta is torque divided by G and J star. So if we plug in our J star for the whole section that we just calculated, we have T over 10.5 lowercase t to the fourth times G. And this is the key really to solving these problems, the rate of twist, because the rate of twist will be the same for each individual segment and for the entire section total, right? So that rate of twist theta is not going to change at all for the entire solution, right? So all segments rotate through the same theta. So with that information, we can go ahead and find the actual torque distribution in each segment, right? Because it's not going to be equal. Some of these pieces are going to take more torque than others, and that will determine the shear stresses in each equation too, right? So, or it's related, it's all interrelated, right? The torque and the shear stress and the J star. So we'll start, let's say, to find the torque. We'll start with AB, all right, and we know theta AB is going to be the same as theta for the whole cross-section that we calculated above. So the torque in AB divided by G and J star just for segment AB, we can set that equal to the total torque divided by G and J star for the total cross-section. And we already noted that J star for AB is 20t to the fourth over 3. So plugging that in, we get 3 times torque in AB divided by 20 G lowercase t to the fourth is equal to the total torque divided by 10.5 times gt to the fourth. Canceling out some of those terms, we get the torque in AB is equal to 0.635 times the total torque. So already we can tell that that first segment, that top segment AB, will take a majority of the torque, right? 63.5%. So then we just repeat this process for the other segments. I'm going to skip to CD. So we have torque in CD over GJ star for CD is equal to total torque over GJ star. And that's all equal to theta, the twist rate. And JCD star is equal to 10t to the fourth over 3. So we get 3 times torque in CD over 10. I'm going to go ahead and eliminate the GT to the fourth values, or you can write them if you want, I guess. That's equal to torque over 10.5 gt to the fourth. So torque in CD is 0.3175 times the total torque. And then since we just have one segment left, right, you could just use algebra to calculate, right, torque minus TAB minus TCD is what's left over. And that's also a good way to verify that you do the calcs correctly, right? So I'm going to go ahead and do the full calc. Torque in BC over GJ star for BC is equal to torque over GJ star, where J star for BC is equal to 12t to the fourth over, we have to cube the 2 in the denominator because it's half, the thickness is half of t, so 8 for that, and then 3 from the formula. So we have 24 TBC over 12 GT to the fourth is equal to T over 10.5 G lowercase t to the fourth. So the torque in BC is 0.0476 times the torque. All right, and then check it. The summation of the individual segment torques should be equal to the total torque. And that does check out. So then the question was asking for the maximum shear stress in the section. Yeah, that's all it was asking for, the maximum magnitude of the shear stress in the cross section. All right, we're gonna do a little bit more than that, but go ahead and note the largest shear stresses. So we'll calculate the largest shear stress in each individual segment. So in AB, the maximum shear stress will be torque in AB times the thickness of segment AB divided by J star of AB. So that's 0.635 times the total torque times lowercase t times 3 divided by 20t to the fourth. That's lowercase t. So that gives us 0.0953 times torque over lowercase t cubed. And then in the other flange, CD, all right, we're going to use the torque in CD times the thickness of CD divided by J star of CD. So we had 0.3175 times the total torque for that. Thickness, and then 3 all in the numerator, and 10 lowercase t to the fourth in the denominator, which also gives us 0.0953 times torque over t cubed. So interestingly, those two flanges have the same shear stress, maximum shear stresses in them, even though they resist different levels of torque, right? But that also makes sense because they have different lengths, or so they have different lengths. So one will naturally be able to handle more torque than the other. All right, so those are the flanges. And then for the web, which is BC, the vertical segment, the maximum shear stress in BC will be torque in BC times thickness of BC divided by J star of BC. And that is 0.0476 times torque times thickness over 2 times 3 times 8 divided by 12 thickness to the fourth, which is 0.0476. Here I ran out of room. That's the nice thing about these devices. Times torque over thickness cubed. All right, so the maximum shear stress in this example occurs in the outer fibers of the two flanges, right? And we also can note that the thickness of the web is equal to half of the thickness of the flanges. So I'll just note max shear stress is 0.0953 times torque over T cubed in outer fibers of the flanges. And then another note or observation that is not specific to this example, but will be always true for problems like these thin-walled open sections. The maximum shear stresses extend along the length of each segment at the outer fibers. So that's something that is always true. Any questions? Okay, good deal. Well, that's everything I have for you today, so perfect timing.